Algebra Unit 11-1, Exponential Functions, Notes and Video 1. An exponential function is a function of the form y equals ab to the x power, where a cannot be 0 and b is greater than 0, and also b cannot equal 1. In an exponential function, a is the initial or the starting amount, and b is the rate at which the function is growing. Those are two huge important pieces, so probably underline or highlight that. A is the initial or starting amount, and the b, the thing that's being raised to that exponential power, is the rate at which the function is growing or decaying. So growth means to get bigger, decay means to break down or get smaller. Notice that the base is a constant and the exponent is now our variable. We've never seen this before. The exponent is what is changing, what is the variable. Exponential functions are non-linear. Again, so we're going to have things that are not straight lines. In the key concept, the words. An exponential function is a function that can be described by an equation of the form y equals ab to the x power, where a cannot be 0, b is greater than 0, and b also can't be 1. So here are three examples. Y equals 2 times 3 to the x power. A would be 2, and b would be 3. Y equals 4 to the x power. A would be 1, b would be 4. And the third one, y equals 1/2 to the x power. A would be 1, and b would be 1/2. Notice the variable, the thing that is unknown, is always the exponent, because it's exponential. All right, our first problem here. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells. Suppose this strand of bacteria doubles every hour, and you start with 3 strands of bacteria. Complete the table and create a graph showing the number of bacteria over the interval where x is greater than or equal to 0 and less than or equal to 4. Then find the domain and range of the function. Alright, so just in this sentence alone, doubles every hour is our rate, and it literally says you start with 3 strands of bacteria. So that's our A and that is our B. So if we were using the formula for that, we'd want to first denote those and make sure we have those. Okay, so it doubles every hour, but we're starting with 3. So in this chart, after 0 hours we have 3 because that's what we're beginning with. So it doubles every hour. So 3 doubling would be 6. 6 doubling would be 12. 12 doubling would be 24. And 24 doubling would be 48. From there we need to graph these points here. Remember, we have our ordered pairs on the graph. So do your best. And again, this is not linear, so we're going to use an estimated and a smooth curve between these points. We are not going to have exact lines or need a ruler at all. So our first point is 0, 3. So again, we're going to have to do our best to estimate. So the 0, 3 is going to be right around there. Our next is 1, 6. So that's going to be right there. 2 and 12. 3 and 24. 4 and 48. Alright, so that would be our curve. So now we're going to make a smooth curve. Again, no rulers. Slowly connecting those. Okay, now, again, you're doing some estimates, so I'm just examining the y-axis. If you missed that, I start at 0 and get to 10, so we're counting about 3.3 or 3 1/3 per line, so I did my best to estimate those. Alright, so now we're doing a real world problem. We're talking about bacteria. So we need a domain and a range. And again, actually, if we're talking about this interval here, then we should not have an arrow on the bottom of our line, because we're only going to 4. Because of this interval, we should not have an arrowhead. So, okay, so we're talking about the domain. So domain are all of our x values. So we're going to go back to do notation. So our domain is x such that, and our range is going to be y such that. Alright, so domain are x values. Well, our original is at 0 hours, and we're going up to 4. So I'm literally just moving that interval down. 0 is less than or equal to x, which is less than or equal to 4. And then my range, so I'm talking about my y values. So here is the y-axis. We need to talk about from where we start here to where we end here. So our first y is 3, which is less than or equal to x, which is less than or equal to 48. And all that again is review from a while back, but it's good to go over. Alright, let's do some more problems here. Graph each exponential function, identify a and b, then state the domain, range, and end behavior. Alright, so our function for this one is y equals 3x. So remember, our formula or parent function is y equals ab to the x power. Alright, so in our given function y equals 3 to the x power, a is 1 and b is 3. So our initial value is 1 and our rate of change is 3. Alright, in order for us to find the domain, the range, and the end behavior, we need to first make a t-chart and figure out what kind of points we're going to have on this chart. So I'm going to make some room here at the bottom. So I need to find some values of x and some values of y. So let's just do some thinking here. As x changes, or as x increases, the y, the output, is going to be really, really big. So let's start with maybe a couple negatives here. So let's say -2, -1, 0, 1, 2. We'll go with those, maybe 5 points. Alright, so if I plug those in, 3 to the -2nd power. So remember our laws of exponents, and we have negative exponents, we move them to the denominator. So I should get 1/9. So 3 to the -1 would be 1/3, or yes, just 1/3. 3 to the 0 power, anything to the 0 power is 1. 3 to the first power is 3. 3 squared is 9, and maybe we go one further. 3 to the 3rd power is 3 times 3 times 3, which is 27. So there's our points there. Alright, now if we're looking to graph these, I'm just getting a little hesitant on, I really can't graph that. It's so small, super small. 1/3 I can estimate it, but it's still pretty small. So it's almost like those points exist, but it's almost like I don't want to use them. This looks good, this looks good, this looks good, and this is still good, but notice again that I'm growing huge numbers here. I mean, if I kept going where x is 4, I'm going to get up to 81. So we're going to get really, really big really, really quickly. So let's graph these the best we can. Now, again, it's a rough estimate, but I don't want to modify my units in any way. I want to count by 1 on this x and y axis. Alright, so the first point I'm going to do is 0, 1. The next point I'm going to do is 1, 3. and then 2, 9. Okay, and then that's really all I can fit in there. So then let's go back and let's do this one that we thought was kind of small. Let's do -1 and 1/3. And then if we were to look at the one other one that's super, super tiny, -2 and 1/9. Maybe somewhere way down here. All right, now when you think about again that we need to connect these dots with a smooth curve. So if I follow these a smooth curve this way, that looks pretty good. Remember, we don't want it to look like a quadratic, so we don't want to do that. We also don't want it to look like a straight line. We don't want it to do anything, or a slightly curved line. This is increasing very, very rapidly. All right, so again, I'm going to connect these with a nice smooth curve, and remember, this is growing rapidly, so I'm going to continue my arrow going upward on the right-hand side. On the left-hand side, this is continuing straight along here, getting closer and closer to the 0, and never dropping below the 0. Remember, you can put this in your calculator, put the function y equals 3 to the x power right in the calculator, and you can see the graph itself. You can go to the table and see, but no matter what values for x you put in, it never drops below the 0. Again, because of those laws of exponents and the negative exponents. So here is my function drawn. So my domain again is the x values. So x such that, and my range are the y values. Okay, so now if we go back and look at the x values. So our x-axis and our y-axis. Our x-axis, it looks like the arrows are telling me this is going on forever. So we could say that x equals all reals. Another notation from the past that we've used is that negative infinity is less than x, which is less than positive infinity. And then both of those will work. And for the range, or the y values, again, nothing drops below 0 on the y-axis, and it goes up forever. It's growing again forever on the y. So y such that y is greater than or equal to 0. We can conclude our range. Actually, and it's not. It's y is greater than 0. Remember, it doesn't actually come in contact with the 0. The last thing we need to fill out is the end behavior. So as x increases, what happens to y? So I'm going to change my color here. So as x is increasing, what's happening to y? It's also increasing. And as x decreases, y does what? So again, changing the color as x is decreasing, so x is getting smaller and smaller and smaller and smaller. What is happening to y? Well, here y is approaching 0. And that is our first example. Right on the back, notice that the previous function never passes through the x-axis. Again, it gets closer to 0, it approaches 0, but it doesn't actually cut through or equal 0. Remember, the equation for the x-axis is y equals 0. We know that. The function approaches the line y equals 0, but it doesn't ever intersect, ever. This means that there is a horizontal, what's called asymptote, at y equals 0. An asymptote is a line that a graph approaches. So since the graph of the function approaches 0 but never actually hits it, we're going to call that a horizontal line or a horizontal asymptote because it's approaching that line. All right, letter B. Y equals 1/2 x. All right, so in this case, A is 1 and B is 1/2. So again, for us to get this on the graph, we can use our calculator. I'm also going to show you the table of values or the t-chart. And I'm just going to kind of start with the basic ones. So I'll do a couple negative, 0, and a couple positive. and we're going to plug those in. So 1/2 raised to the negative 2. So that means, again, the laws of negative exponents is I'm going to move them to the opposite side. So I'm really going to get 4 as my output. I'm going to get 2 as my output. I'll get 1. I will get 1/2. And I'll get 1/4. So now, alright, now in case you're not capable of keeping up and doing that in your head, then you need to show work here. But all of this is old stuff, so let's just do 1. So y equals 1/2 to the x power. So y equals 1/2 to the negative 2 power. So that negative exponent we're going to get rid of first. So we get y equals, since this negative 2 is being distributed to both the top and the bottom, we would get 1 to the negative 2 over 2 to the negative 2. And one more time. A negative exponent means we move to the opposite side of a fraction, so now we'd get 2 squared over 1 squared, which again gets us 4 over 1, which is 4. So that goes way back many, many units ago, and even a lot of last year. So that's how I got those outputs. So if you need to show all that work, you can. You can use the calculator. But again, we are way beyond that, so I'm hoping we can do some of that in our head or just use the calculator. Alright, so now if I'm going to plot these points, get negative 2, 4. Okay, and then I got negative 1, 2. Got 0, 1. 1 and 1/2, 2 and 1/4. Again, if I was to connect these, this side is continually going up and getting bigger and bigger and bigger and bigger. And this side is coming down, and again, it's going to come very close to 0, but it's not going to interact with it, and it's not going to go past it. Alright, so the asymptote here is y equals 0, just like the one before, because we're getting this idea of a straight line right here at 0. Our domain Alright, so our domain is all possible values of x. So it looks like x is increasing forever in the negative infinity and forever to positive infinity. Again, we can also use the all reals abbreviation for that as well. So now we're talking about the range, so the y values. We're approaching 0 and we're going positive, or I'm sorry, we're approaching 0, but we're still growing to the positive y's. So where y is greater than 0, again not equal to, because it's never going to actually touch. Our end behavior, as x increases what is happening to y. So I'm going to change colors again. So here is how x is increasing. What's happening to the y? It's approaching 0. And then for as x decreases, so x is large and x is decreasing going back this way. So as x is decreasing, y is actually increasing. And that is letter B. Alright, I would like you to try C and D on your own. Just because they look a little bit different, that it's no reason to panic. We're still doing y equals a to the bx. And we're for both the C and D. So try those on your own the best you can. Again, use all the knowledge you've learned from this lesson and previous years. And even the beginning of this year, as x and y increase and decrease, you can do those. Domain and range, you know those. The only new piece is deciphering A, B, and the asymptote. Asymptote is just a line that the graph or the function is approaching. And A and B is just the starting and the rate of change, or the initial and the rate of change, which you can also do. So good luck. And again, if you're having trouble, just bring it up in class. Alright, finally some word problems. Answer the following questions. Letter A. The height in feet, f of x, of a bouncing ball after x bounces is represented by f of x equals 80 times 0.5 raised to the x power. How high is the fourth bounce? So x is the number of bounces, and height would be the output of the f of x. So I really need to find f of 4. So 80 times 0.5 raised to the fourth power, and I'm just going to calculate that in my calculator and get an answer. So remember, to raise to the fourth power, you want to use that caret key on your calculator. So we should get f of 4 equals 5. So our answer is 5 feet. Letter B. Graph f of x equals x squared and g of x equals 2 to the x power for x is greater than or equal to 0 on the set of axes below. State which function f of x or g of x has a greater value when x is 20. Justify your reasoning. So we'll first graph x squared. So hopefully you remember that is something interesting. That's from last unit. X squared is the quadratic function. And where 2 to the x is now the exponential, because the exponent is in the exponential position, or exponent position. First I'm going to color code these. F of x I'm going to do in blue. G of x I'll do in green. So x squared. So if I pick 0, 0 squared is 0. If I pick 1 for my x value, 1 squared is 1. If I pick 2 as my x, 2 squared is 4. If I pick 3, it's 9. If I pick 4, it's 16. And I can't go any higher than that, so let's connect these with a smooth curve. That's not a smooth curve. Okay, and then g of x is 2 to the x power. So again, maybe I'm using my calculator for this. I can always make the table of values. So 2 to the x power. So first let's say 2 to, and so since I'm in quadrant 1, I don't need to worry about negative. So I again can do a lot of this in my head. So 2 to the x power. Let's start with x being 0. So 2 to the 0 power is 1. Next one, let's plug in x is 1. So 2 to the first power is 2. Let's plug in 2 now. So 2 to the second power is 4. Then let's plug in 3. 2 to the third power is 8. And let's plug in 4. We get 16. Alright, and now if we connect these again with a smooth curved line. Okay, they kind of look similar, but they are different. State which function, f of x or g of x, has a greater value when x is 20. Justify your reasoning. Alright, so that's what they look like. So right now I really can't tell. So let's try this instead. Let's go over here and show some work. So first, f of x, but I want to try where x is 20, so I'm going to do x of 20 equals x equals 20 squared. So f of 20 is 400. And then let's try g of x. So g of 20 equals 2 to the 20th power. So g of 20 equals, and this is definitely what I'm going to have to use on my calculator. Alright, and we would get so 1,048,576. So although this graph is kind of misleading in that they both look like they're kind of going to be the same towards when we get to 20, because we really can't tell really what's happening after this. Like anything could happen. So if we actually plug in our values for x, plug those in, we can get a real output and get an actual value. So which one has greater value? Our answer would be g of x, and the reason is because we actually found the values. Alright, let's see. Letter C and D. We'll do C together and then you can do D on your own. Letter C. John bought a car for $25,000 in 2014. The function v equals $25,000, so that's our A, that's our initial value, times 0.82, so that's our rate of change, raised to the t power, minus the depreciation. So depreciation means when a price gets lower or something loses value. So there's a common phrase that as soon as you buy a car and you drive it off the lot, it depreciates value. You lose value. That happens with most things that we buy, just because technology just keeps evolving so quickly. Where V represents the value of the car in dollars and T represents the time in years since 2014. What will the value of John's car be in 2019? So V is the value of the car. We don't know that. We're going to leave it alone. But we know that the car started at $25,000. The rate of change is always going to be 0.82. So now T is time. So we need to know time in years since 2014. So if it started in 2014 and they want to know 2019, how many years is that since 2014? Well, that's 5 years, so I'm going to raise it to the 5th power. So again, use this in my calculator. V equals $2,500 times 0.82 raised to the 5th power. Alright, when we plug that in, we're going to get $9,268. And we'll just round, because this is money, we'll round to the nearest 100th place, and that makes 50 cents. Alright, I'd like you to try letter D on your own. Good luck.